Hello again. This is Math 2-115 coming to you from the College of DuPage. This is the conclusion of the lecture entitled Definitions and Calculations Using Big O, Omega, and Theta Conventions. As always, please be an active learner while watching this video. When we adjourned last time, you were working on this problem. How can Big O notation be used to estimate the sum of the first in positive integers? If you solve this, congratulations. If not, I will let you go after it again. You know what to do. Let's see how you did. Well, because each of the integers, the sum of the first in integers, does not exceed n, we can replace all of these numbers with n. So this is n plus dot 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 plus n. I have n terms in the sum, and each one of them is n. So that is n times n, or n squared. So from this inequality, it follows that 1 plus 2 plus 3 plus all the way up to n is big O of n squared, because we can have KB1 and CB1 as witnesses. In this example, the domains of the function in the big O relationship are the set of positive integers. We can also give big O estimates for other standard functions, like the factorial function and the logarithm of the factorial function. Now recall, the factorial function is f of n is equal to n factorial, and you take 1, multiply by 2, multiply by 3, all the way up to n, that is n factorial. And this is defined when n is a positive integer and 0 factorial is 1. So you see, this is how it grows. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, and by the time you get to 20 factorial, you have an enormous number. It grows really fast. So if you wanted a big O estimate for n factorial, it would have to be something big. But you can say n factorial is equal to this, and each of these n integers is less than n. So I can replace it by n, and I have n factors of n, or that's n to the n. So n factorial is big O of n to the n. Now this inequality also shows, if I take logarithms of both sides, what will happen is, if I take logarithm of the side where I'm pointing at, you'll have log of n factorial. And when I take the logarithm of this side, I'll have log n to the n. But log n to the n, property of logarithms say I can bring that n out in front, and so I have this. So this also implies that log of n factorial is big O of n log n. And again, we're taking c to be 1 and k to be 1 as witnesses. Now, you can show by induction, I think we actually did show this by induction, that n is less than 2 to the n whenever n is a positive integer. This inequality is going to imply that n is big O of 2 to the n, and we're going to use this inequality to show that the natural logarithm of n is also big O of n. So let's begin. This is the inequality that we know is true from induction. So we can quickly conclude that if we take k to be 1 and c to be 1, we can take the logarithm of both sides. And we're taking the logarithm base 2 of both sides. So I get the logarithm of n, and that's logarithm base 2, is less than, and when I take the logarithm base 2 of 2 to the n, I get n. So this statement right here, with k equals c equal 1 as witness, tells us that the logarithm base 2 of n is big O of n. And again, we can take those as the witnesses. Now, if we have logarithms of a different base, we can use the change of base logarithm. So this is a logarithm base b of n, and that is, by definition, you can prove this. This is the logarithm base n divided by the logarithm base logarithm of, and this is logarithm base 2 of n divided by the logarithm base 2 of b. But you see, we've already shown that the log of n is less than n. The denominator is the same. So I have an inequality going this way. So you see, this logarithm, base b of n, is big O of ln of n, and it's logarithm base 2 of n, divided by the logarithm base 2 of b. And so you see, we can prove relationships about exponentials and logarithms this way. And in fact, these are things now that to do a rigorous proof of some of this, you need calculus, but we can understand that the function that's 1 is just flat. Logarithm grows, but very slowly, and it grows more slowly than n grows. N is just a line that's going out, but n grows slower than n log n. That grows slower than n squared, and that grows slower than 2 to the n. So this is some growth of functions that are commonly used whenever we're doing big O estimates. Now we're going to cover some useful facts that help us determine whether big O relationships hold between any pair of functions when each of the functions is a power of a logarithm, either a power or an exponential function of the form b to the n, where b is greater than 1. And the proofs of these do involve calculus, but you don't have to be able to prove these to understand them. Okay, so previously we talked about if f of n is a polynomial of degree d, that means the biggest exponent was d, then f of n is big O of n to the d, where d is the order of the polynomial. Applying this theorem, we can see that n to the c is big O of n to the d if d is bigger than c is bigger than 1. But it doesn't work the other way about. You should think through these. In example 7, we showed that the logarithm base b of n was big O of n when b was greater than 1. And if we raise sides of that relationship, one side to the c and the other side to the d, where d is a bigger number, you'll see that the natural logarithm, it's not natural logarithm, it's the logarithm base b of n to the c is big O of n to the d. But it doesn't go the other way. Again, think through these. This tells us that every positive power of a logarithm of n to the base b, where b is greater than 1, is big O of every positive integer of n, but the reverse is not true. Previously, we showed that n was big O of 2n. More generally, when d is positive and b is greater than 1, we know that n raised to the d is big O of b to the n, but not the other way about. This tells us that every power of n is big O of every exponential function of n with a base that is greater than 1, but the reverse never holds. And lastly, whenever c is bigger than b is bigger than 1, b to the n is big O, c to the n, but c to the n is not big O of b to the n. Now, sometimes we'll be combining these, but this last one tells us that if we have two exponential functions with different bases greater than 1, one of these functions is big O of the other one if and only if the base is smaller or equal. Now, many algorithms aren't simple. They're made up of two or more separate sub-procedures. And so what we're going to do is we're going to estimate the number of steps term by term and add them together, but we're using big O estimates for the whole thing. So here is a problem I'd like for you to work on. This is a proof. Suppose that F1 is big O of G1 and F2 is big O of G2 of X. Then F1 plus F2 of X is big O, the maximum of the absolute value of G1 X plus, not plus, the maximum of these two things. So it is the maximum of G1 of X and G2 of X, the absolute value. You know what to do. Let's see how you did. Well, okay, so F1 is big O of G1, so this is true whenever X is bigger than K1. And the other one is true whenever you're bigger than K2. So if we take the bigger of K1 and K2, we can say that the absolute value of this is equal to this, is less than or equal to this by the triangle inequality. And when X is greater than both of the K's, K1 and K2, then we have this, that this is less than or equal to this, which is less than or equal to this. I can take the C1 plus C2, certainly this is less than C1 plus C2 in each case, and I can factor out the G, and I get this. Now G in this case was the maximum of the two. So what we were able to do is say, yes, we can do this kind of calculation whenever we're adding functions and using big O notation. We often have big O estimates for F1 and F2 in terms of the same function G. We didn't in the last example, but often we do. In this situation, and this is called a corollary, suppose both of these functions are big O of the same function G of X. Then this sum of these functions is also big O G of X, because these are going to be the constant grows by 2 that we need. In a similar way, big O estimates can be derived for the product of two functions. So the product of two functions is equal to this, less than or equal to this. C1, C2 are put together, and I have this product, and that's less than this. So what this means is that it follows that F1 and F2 is big O of G1 and G1, G2, because there are constants C and K, namely C is C1 times C2, and K is the maximum value to make that true, such that this is true whenever X is greater than K. And this is a theorem, and this is what it says. So if F1 is big O of G1 and F2 is big O of G2, then the product F1, F2 is big O of the product G1 and G2. Now the goal in using big O notation, an estimate function, is to choose a function G of X that is as simple as possible, and that explains the growth, and the growth is relatively slowly, so that f of x is big O of G of X. And so what we're going to do is we're going to do some calculations where we have multiple steps to look at. Okay, so suppose I ask you to give me a big O estimate for f of n equal 3n, this is the log of n factorial, plus n squared plus 3 times log of n, and n is a positive integer. We're going to do this term by term. So looking at the first one, we have a product. And so what happens is that this is going to be the logarithm part of this. Logarithm of n factorial is big O of n log n. So this is big O of n log n. But we know that 3 to the n is a big O of n. So we're taking big O of n times big O of n log n, and that gives us big O of n squared log n. Again, think about this. Next product term has n squared plus 3 times logarithm of n. Now, if n is bigger than 2, n squared plus 3 is less than 2n squared. So it follows that n squared plus 3 is big O of n squared. Thus, from a previous theorem, we know that this product is big O of n squared log of n. So now what we can do is we can define the two estimates that we had for the first term and the second one, and this shows that f of n equal 3n logarithm n factorial plus n squared plus 3 log n is big O of n squared log n, because they both are. Let's look at another example. Give a big O estimate for f of x equal x plus 1 log x squared plus 1 plus 3x squared. Now, The 3x squared is pretty easy to do because 3x squared is big O of x squared. The first term, though, is a product, and so if we look at this one, we have x plus 1 log x squared plus 1, and x plus 1 is big O of x. And furthermore, this is less than, if we pick x to be bigger than 1, this is, so x is bigger than 1, so if I take x squared, it's also bigger. So this is x squared plus x squared is less than or equal to 2x squared. So you see this is less than this, and the sum of the logs is the logarithm of the product is the sum of the logs. So this is log 2, and this is 2 log x. So if I combine this expression with the other expression, I can say this is less than or equal to 3 log x if x is bigger than 2. This shows that this logarithm of x squared plus 1 is big O of log of x. So the whole thing then is this whole entire expression is big O of x log x. So f of x then is big O of x squared, because log of x times x is less than or equal to x squared. Again, you want to think through these, make sure that you can follow each and every step. Okay, now it turns out that sometimes it's important not just to have an upper bound, which is what the big O notation does, but we sometimes need a lower bound too. It will take somewhere between the lower bound and the upper bound for the algorithm to work. And to address this, we introduce a new thing, and this is something that Knuth did, but this is called the big theta notation. And again, he did this because people weren't paying good attention to this. And here's the definition of big O of omega, and then we'll define big O of theta. So let f and g be functions from the integers, or the set of real numbers, to the set of real numbers. We say that f of x is omega of g of x if there are positive constants c and k such that the absolute value of f of x is bigger than or equal to c, the absolute value of g of x, whenever x is big enough, whenever x is bigger than k. And so the way you read this again is f of x is big omega of g. Now there's a strong connection between big O and big omega. In particular, this is what it means. F of x is omega of g of x if and only if g of x is big O of f of x. Again, you want to think about this, and you can verify this using just the definitions. Let's look at an example. So the function f of x equal 8x cubed plus 5x squared plus 7 is omega g of x, where g of x is just x cubed. Because if you look at this, this is going to be bigger than x cubed. You're adding positive numbers to it. So it's easy to see that it goes this way. And again, I'm just saying, since there's 8x cubed, this is bigger than or equal to 8x cubed, because you're adding positive things to it. So those can be your witnesses. And so this is equivalent to saying that g of x equal x cubed is big O of 8x cubed plus 5x squared plus 7. And so we're using this definition to think about the lower bounds. Now, often it's important to know the order of growth of a function. And in fact, it's possible for something to be bounded above and below by the same function. And that means it's caught in between, and it behaves bounded by that. So that motivates this definition of big theta. Let f and g be functions from the set of integers, or the set of real numbers, to the set of real numbers. We say f of x is big theta of g of x if f is big O of g, and if f is big O of g, and f is omega of g of x. When f of x is omega of g, we say that f is big, and that was theta, not omega. We say that f is big theta of g of x. That is, f of x is of the same order as g of x. So f of x and g of x are of the same order. So when f is big theta of g of x, it is also the case that g is big theta of f of x. That follows from the definition. And also note that this means if f is big theta of g of x, if and only if you got real numbers c1 and c2, such that f is sandwiched in between the two whenever x is bigger than k. Now, we showed in a previous example that the sum of the first integers was big O of n squared. I ask, is the sum of these integers also of the same order as n squared? Well, here we've got one way we have to check to see if it's actually the other. So we let f of n equal the numbers 1 plus 2 plus 3 all the way up to f of n. Now we already know that it is big O of n squared. So what we have to do is we have to find, or try to find, a constant c such that f of n is bigger than c n squared if k is large enough. Well, to obtain a lower bound for this sum, you could ignore the first half of the terms and sum only the terms greater than the greatest integer less than or equal to n over 2. So we say that this sum is bigger than, now I just take the last half of these and I get that, so this one is bigger, and that's bigger than or equal to. And now what I can do is I can say that all of these numbers that I have up here are bigger than or equal to the smallest of these numbers. And whenever I write what this is, what will happen is I can factor out this greatest integer of n over 2, and what I will have is n, how many of them do I have? And I have n minus n over 2 plus 1, which is bigger than or equal to, and this is going to be n over 2, and that is going to be, those will subtract, and I get n over 2, which is n squared over 4. Now notice that what I have is that this then is bigger than or equal to 1/4 n squared. So you see I bounded it below and I bounded it above. So this shows that f is both, this shows that it was omega of n squared, but previously we showed that it was big O, so that means it's of the same order. Now here's another problem for us to talk about. Show that this thing, 3x squared plus 8x log x, is theta of n squared. Well, 8x times log of x is between 0 and 8x squared. So it follows that 3x squared plus 8x log x is less than, this one is 3x squared, that's less than 8x squared, so this is less than 11x for x greater than 1. Consequently, this entire expression is big O of x squared. And clearly, that x squared is big O of this because you're adding more positive numbers to it. So consequently, this is theta, the same order as x squared. Now, one useful fact is that the leading term of polynomial, I think we actually already talked about that, determines its order. And so, you know, we can just look at this and tell that this polynomial is of order 8. This polynomial is of order, this polynomial is of order 8. This polynomial right here is of order 19. And this one is of order 99. Now here is an LSA 8 for you, and these are 1, 2, 3, 4, 5, 6 problems where I'm asking you to do things. You can read them. These will be posted in your Grace Notes for your reading at your leisure. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.